So let's do the proof here, or rather let us do the proof. The proof is once again a simple application of the multivariable Jacobian transformation. So let us define u1 to be x bar minus mu, and ui is xi minus x bar. In which case, then ui plus u1 is simply xi minus x bar plus x bar minus mu is just xi minus mu. So xi minus mu is ui plus u1. And then next is x1 minus mu can be written in terms of u1 minus a linear combination of the ui. And so let's check that. So we have here is that u1 minus summation of the ui, I from 2 up to n, can be written as x bar minus mu minus summation I from 2 up to n of xi minus x bar. But let us note the following. Summation I from 1 up to n of xi minus x bar will be equal to 0. Check this. Of course, it's quite straightforward. So in that case, we therefore have summation I from 2 up to n of xi minus x bar is therefore nothing more than summation I from 1 up to n of xi minus x bar minus x1 minus x bar. In that case, we therefore have that x bar minus mu minus summation I from 2 up to n, this part we know is already 0, of xi minus x bar is nothing more than x bar minus mu minus x1 minus x bar, minus of a minus. And so that is x bar minus mu plus x1 minus x bar is x1 minus mu. So that's what we claimed here. x1 minus mu is u1 minus the sum of the ui. So next is what? So this allowed us to go from u1, u2 up to un back to x1, x2 up to xn. So the joint PDF for u can then be written as the joint PDF for the x, which is this part here, multiplied by the determinant of the Jacobian. That is just because, as we see, let us just go back. Xi minus mu, we have PDF that is xi minus mu is normal, means 0, variance sigma squared. So it has PDF which is 2 pi sigma squared minus 1/2 times exponential of xi minus mu squared divided by 2 sigma squared. So that is why you have 2 pi sigma squared as an independent. You raise the power n over 2 and you take the product of this quantity. So now you may say, what about the Jacobian? But what about it? So the Jacobian, the determinant of the Jacobian does not depend on u. That is because the Jacobian is linear. So the Jacobian looks like this. The inverse transformation looks like xi is some linear combination, summation of, say, like, so as we see, the, say, x2 minus mu is, say, like u2 plus, say, u1. So the derivative of, say, x2 minus mu with respect to, say, u1 is minus, is, say, like 1, and the partial of x2 minus mu with respect to u2 is equal to 1 also. Both of these does not depend on u 1 or u2 or dot dot dot. So in a sense, the Jacobian here does not depend on u. That is a very important thing to note. So in any case, we have this is a joint PDF for u. And we note is that xi minus mu is equal to ui plus u1 for I from 2 up to n. So that's why you product from I from 2 up to n. And then the case when x1 minus mu, as we said earlier, is u1 minus summation of I from 2 up to un of ui. And so that is, this part is for x1. And then now if you simplify this out, you will see that this product can be factored into two terms. One term depending only on u1, and the other term depending on the sum from 2 up to n of the ui. So the joint PDF factors into the product of one PDF for u1 and another joint PDF for u2 up to un. So what that implies is by independence, we can conclude that fuu as a product of a function that depends only on u1 and another function that depends on u2, u3 up to un. So in other words, u1 or random variable rather u1 is independent of v, which is u2 up to un. And this is quite true because as you can easily see, what this basically just means is that if I take the integration of the joint PDF, f say like in any set A, of say like f of u1 up to un, I can write this as the integration with respect to some function, let's say g of u1, du1, and some function of say like h of u2 of the un of du2 up to dun. So by this fact, this event is independent of this collection of events. And that implies that the random variable u1 is independent of the remaining random variables. And this is finally the last trick. So the sample standard deviation, which we defined earlier, n minus 1 times s squared, is a sum of xi minus x bar squared. And as we remember, x1 minus x bar can be written as, in that case, if we remember correctly, that can be written as, technically speaking, we can write that as x1 minus mu plus mu minus x bar okay, and let me see here. Xi minus x bar squared can be written as x1 minus okay. Yep, okay, yes, let's go back. Yeah, okay, so u1 is ui is xi minus x bar. Yeah, we said earlier is that, yes, x1 minus x bar, as we say earlier, right here. Summation I from 1, no, summation of xi minus x bar is equal to 0. So therefore, summation of I from 2 up to n of xi minus x bar, which is just ui, summation of ui, has to be equal to x1 minus x bar. That's what we show here. this part right here. So therefore, x1 minus x bar square can be written as a summation of the u2 from ui from 2 to n. And similarly, xi minus x bar summation I from 2 to n is also a function of ui square for I from 2 up to n. So s square is purely a function of the random variable u2, u3 up to un. So because u1 is independent of u2 up to un, and because u1 is equal to x bar minus mu, so therefore we have that x bar is independent of s square, because s square is a function of u2 up to un. So in summary, x bar is independent of s square as we claim. So it may look, say, a bit daunting, but really at the end of the day, it is nothing more than a simple argument in terms of the multivariable Jacobian. So with that result now, we could easily prove the following tour de force. Now with that result in place, it is now a simple exercise to show that if you have a bunch of random variables, x1 to xn, they are independent and they all have the same distribution, which is normal, with mean mu and variance sigma square. Then the sample mean is independent of the standard deviation. And furthermore, the standard deviation or the sample variance properly transformed is chi-squared with n-1 degrees of freedom. And this is, as we claim, a quite easy exercise. So let's start out with this simple observation here. Summation I from 1 up to n, xi minus mu divided by sigma squared. Add and subtract x bar to get this term. And as we remember, summation of xi minus x bar minus mu will be equal to summation of xi minus x bar, everything multiplied by x bar minus mu. Because x bar minus mu, you can top it up as another constant. You can move outside the sum, and this is going to be equal to 0. So if you expand out this square, you get xi minus x bar divided by sigma square plus n times x bar minus mu divided by sigma square. By expanding out, because the cross term we show is 0. So now let us look at this quantity here. This quantity is nothing more than n minus 1 s squared divided by sigma squared. So that's this first term. Let's call that y. And then this second term, let's call it z. So what do we know? We know that x bar is normal with mean mu and variance sigma squared over n. So x bar minus mu is normal with mean 0 and variance sigma squared over n. So therefore, square root n of x bar minus mu divided by sigma is normal with mean 0 and variance 1. So it's square n times x bar minus mu square over sigma squared is chi-squared with 1 degree of freedom. So that's what we know. Let's look at this term here. This term here is once again quite simple. So xi minus mu over sigma is normal 0, 1. And so because they're independent, this is just a sum of independent normal squared. And so this is chi-squared with n degree freedom. So W is chi-squared with n degree freedom. And now we have W is equal to y plus z. So the last thing we need to note is that because x bar, so W is chi-squared with n degree freedom, and z is chi-squared with 1 degree freedom. Because s squared is independent of x bar, we therefore have, by the independence of moment generating function, that W is equal to y plus z. So the moment generating function for W is the moment generating function for y times the moment generating function for z. That's what we have here by independence. So what that implies is the moment generating function for y is the moment generating function for w divided for t, for z. We know that because w is chi-squared with n degree of freedom, that's the moment generating function for w. This is the moment generating function for z. So simplification gives you this. But this is nothing more than the moment generating function for a chi-squared with n minus 1 degree of freedom. So by uniqueness, y really have to be chi-squared with n minus 1 degree of freedom, as we claim. So in that case, we can then easily see that our statistics, our t statistics here, that you may have seen quite a few times before, by some simplification, x bar minus mu divided by sigma. If you divide the numerator by sigma and you divide the denominator by sigma, things cancel out, nothing happens because of the square root. And this is nothing more than the numerator is once again normal, standard normal. The denominator we claim is chi-squared with n minus 1 degree of freedom divided by n minus 1. So as we saw earlier, this is student t with n minus 1 degree of freedom as we claimed. So this derivation here is, I would say, quite sophisticated. But we see that it includes everything that we have studied in the last few weeks. So in really chapter 4, 5, and 6 build up and allow you to derive this claimed result. And so it's unlikely that any of us can fully understand this derivation the first time we see it, but hopefully if we see it a few more times, maybe in 422 or in later work, we'll realize that yes, we know all the techniques necessary to derive this result. Okay, so that will be our end of the discussion of roughly all the way that is necessary to derive the distribution of functions of random variables. So now let us move to the last topic of 421, and that is order statistics. So it's nice to end with order statistics because I think it brings order to the chaos that is, say, this semester. So order statistics is a very beautiful subject on its own, but like everything else, we don't really have much time devoted to it. So this is section 617 of your textbook. So let's try to maybe give an overview of a few tricks here and there to derive the results of this order statistics. So we start with a collection of independent random variables, and they all have the same distribution. So let us now consider a permutation of this random variable, where we order them as x subscript 1, x subscript parenthesis 2, all the way up to x subscript parenthesis 1. And they're ordered in increasing order. So for example, if I said x1, let's say is 2.1, x2 is 3, and then x3 is say like 0.4. Then x subscript 1 is 0.4, less than x subscript 2 is 2.1, less than x subscript 3, which is 3. So ordering that respect a monotonic increasing order. So x subscript little k, parenthesis, is known as the k order statistics. If we start out with independent random variables, then by ordering them in increasing order, they are now dependent. So we're interested in a few things. First, what's the distribution of the minimum? Then what is the distribution of the maximum? Can we talk about the distribution of a fixed or the statistic, say xk, say k equal to 10 or k equal to say like n divided by 2, or so on and so forth? Can we talk about the joint distribution for say xk and xl for some k not equal to l? So let's start with the most elementary. Let's start with say the minimum and the maximum. So let's derive the CDF for the minimum and the maximum. And there goes as follows. I give you x, be given. Then the minimum is bigger than x if and only if every other value, if all the values is bigger than or equal to x. Because if the minimum is bigger than x, then obviously all the other values has to be bigger than x. Otherwise, if one value is less than, that value will be the minimum. So therefore, the probability that the minimum is bigger than x by independence will just be the product of the individual probabilities being bigger than x. And that is, as we see, probability xi bigger than x is nothing more than 1 minus fx, which is because fx is the probability that x is less than or equal to x. So in that case, we just have 1 minus fx to the power of n. So the probability that x1, the minimum is less than or equal to x, is just 1 minus that probability. So we have a simple expression for the CDF of the minimum. So we know that this formula here is valid even for the discrete case. So we can derive the PMF for the minimum if it is discrete, or we can also derive the PDF if the xi are continuous. So in generally speaking, for other statistics, the continuous case is easier because you don't have to worry about ties, and because you can take the derivative. So usually, when you look at section 6.7 of your textbook, they will always focus on the continuous case, because the discrete case is quite much more messy, because in the continuous case, the probability, let's say xi equal to xj is always equal to 0 whenever I not equal to j. But in the continuous case, the probability that xi equal to xj is generally bigger than or equal to 0. So ties are harder to handle. So in any case, when the xi are continuous, then you can take the derivative of this quantity to get the marginal PDF for the minimum, the derivative, and that is simply you move n out. You have a minus sign in front, and then you have 1 minus fx to n minus 1, and take the derivative of minus fx, so you have another minus sign here. This cancels out with this, so you just have fx left. So that is the marginal PDF for the minimum. The distribution for the maximum is argued similarly. So for any given x, the maximum is less than or equal to x if only if all the elements are less than or equal to x. Because if one element is bigger than that x, then that element is going to be the maximum. So therefore, the probability that xn less than or equal to x, the maximum is less than or equal to x, is a product that every element is less than or equal to x. So that's just fx to the power of n. And so in the case of continuous, once again, you get the derivative. So the marginal PDF is given simply as follows. So once again, in the discrete case, things are harder just because of ties. So let's see the quick example. Suppose I have a bunch of independent uniform on 0, 1. Then the maximum has the CDF of the form fx to the power of n, and because fx is just x, you get x to the power of n. So if I let x be 1 minus theta divided by n, then the probability that the maximum is less than 1 minus theta divided by n is simply this quantity to the power of n. And so as n goes to infinity, it converges to e to minus theta. So rearranging the above, move n here. We have n times 1 minus xn bigger than theta converges to e minus theta. And this is nothing more than the probability that the exponential 1 is bigger than or equal to theta. So in that case, the maximum converge, properly transform, converge to exponential with rate parameter 1. Similarly, you can show that the minimum also converges to exponential with rate parameter 1. So the key point here is that this result here is exact, but by letting n increases, you can get something that converges to exponential. So that's the first example. Let's look at another example. Suppose, so uniform give you exponential. So now let's start with exponential. What do we have? Well, the probability that xn less than or equal to x, we know that is probability that x less than or equal to x, which is fx, is just going to be 1 minus e minus x. So therefore, the probability that the maximum, this should be the maximum, this should be the parenthesis here, the probability that the maximum is less than x is 1 minus e to minus x to the power of n. So now by taking x, which is theta plus log n, we will have that xn, once again, the maximum. I will fix the typo. Xn less than theta plus log n is 1 minus exponential of this term. And by using the properties of the exponential function, that's e minus theta divided by n. And so you take the nth power of this one, that converges to e to the minus of e to the minus of theta. This is known in the literature as a Gumbel distribution. So you can take a look at, say, Wikipedia, but in any case, the maximum converges marginally to a Gumbel distribution. In contrast, the minimum, the probability that the minimum is bigger than or equal to x is, as we say, 1 minus fx to the power of n, and due to the exponential function, 1 minus fx is nothing more than e minus x. So we have e minus x raised to n power, that's e minus nx. And this is nothing more than exponential with rate 1 over n. So the minimum turns out to have the exponential distribution, but the maximum turns out to have the Gumbel distribution. So for the same distribution, the minimum could have a distribution that is very different from the maximum. You see that in the case of the uniform, the minimum and the maximum have similar distribution, both converging to exponential. But in the case of exponential, the maximum converges to Gumbel, but the minimum is always exponential. So it turns out that the distribution of the maximum and the distribution of the minimum has quite a lot of very interesting properties that has been studied over the years. So let's look at another example. Suppose now I have, from exponential, I get Gumbel. So the Gumbel has this as the CDF. So the PDF of the Gumbel, is going to be e minus theta, e minus theta, or rather let's replace it with e minus x of e minus x. So that is the PDF of a Gumbel with location parameter mu equal to 0 and scale b equal to 1. And you can look for the more general definition of the Gumbel on, say, Wikipedia. So if you have independent exponential, the maximum looks like a Gumbel. So now I suppose I start with independent Gumbel. Then what do I have? Well, once again, by the PDF, that's exponential e minus x to, and then that's the PDF here, CDF, fx to the power of n. So I could move the n out here, And if I let x be theta plus log n here, then after some simplification, I still have back e to minus e minus theta, which is once again the gumball. So the maximum of a bunch of gumball is gumball. The maximum of a bunch of exponential is gumball. So it turns out the gumball is quite special distribution. It turns out that the maximum of independent normal was a big gumball. More interestingly, the Fisher-Tippett-Grenenko theorem, which is a classic theorem in order statistics, states that the maximum of a collection of IID continuous random variable, independent and identically distributed, the maximum of n random variable with the same distribution, the independent, converge either to the gumball distribution, which we just saw, converge to the Weibull distribution, which I think is problem 4.86. I wouldn't say some problem in chapter 4. So the Weibull is basically x to the power of m, where x is exponential and m is bigger than 0. So in chapter 4 we see that the power of exponential is a Weibull. And the Fréchet is another distribution, but you have not seen the Fréchet before, and we will not have time to discuss it. But in any case, the maximum of random variables converge either to gumball, Fréchet, or Weibull. So this is like the analog of the central limit theorem. So the central limit theorem says that the sum converges to normal. The maximum doesn't converge to a single distribution, but the maximum will converge either to a gumball or Fréchet or Weibull, in the case when your random variables are continuous. Okay, so let's just move on and talk about the CDF and the PDF for say x, k for some fixed other k. For say 2 less than or equal to k less than or equal to n minus 1. Because we already talked about the minimum and the maximum, which is k equal to 1 and k equal to n. So now, using the same trick, given a fixed value x, the kth order statistics, the kth value, the k smallest value is less than or equal to x, if and only if at least k of the xi are less than or equal to x. So as we see, x1 less than x2 less than less than xk less than or equal to x. So that what that meant is that at least k of the xi have to be less than or equal to x. So in that case, we can just sum ki from k up to n. So if I have I of the xi, if I have say like j, or let's say I of the xj is less than or equal to x, how many events that happens? I could choose and choose I of the random variable that would be less than or equal to x. And for those, we have a binomial random variable fx to the power of I and 1 minus fx to the power of n minus I. So the idea is as follows, right? Because xk less than or equal to x, what this implies is that out of n independent trials, at least k of them is less than or equal to x, and that has happened with property fx. So fx is p, property of success. Property of success is the probability that it is less than or equal to x. So therefore, by this tail property of the binomial, that is simply this quantity. Out of n independent trials, at least k of them is less than or equal to x. So sum I from k up to n of this one. And now we can use the beta CDF representation. So C chapter 4, I think that is maybe problem, I would want to say problem 4.93, but I don't remember. So let's go back and check here. So that is problem 4.134. Yep. Okay. So that is, I have it right here. Lucky me. So this is problem 4.134. So using the beta CDF representation, I can write it as this beta CDF. And so using even define G to be the CDF for beta, correspondingly, that is just G evaluated at fx. So now this is once again quite easy because I have this as the CDF and that is given by G to fx. Then that is nothing more than in the case when the xi are continuous. So this result is true in general even for the discrete case or continuous case, both of which is true. But in the case when it is continuous, I could now take the derivative. So I could take the derivative of the PDF, of the CDF. So the derivative of the CDF, that's the derivative of G of fx. And the chain rule will tell me that it's just G times the function fx times this to fx. But because G is now beta, capital G is the CDF of beta. So little g is this PDF of beta. So that is the PDF of beta multiplied by fx. And that gives me the marginal PDF for the xi. So you can take a look. I think this is theorem. Let's see. Let me jump to this part of the textbook here. So that is theorem 6.5 in your textbook. So let's go back. This is nothing more than theorem 6.5 in your textbook. So another argument that works in the case when your random variables are continuous. So this only works when the x are continuous random variable. Goes as follows. Suppose I consider a small interval around x. So x minus epsilon up to x plus epsilon. Then the kth order statistics is in the interval if only if k minus 1 of the original xi is less than x minus epsilon, and the remaining n minus k of the xi have to be bigger than x plus epsilon. So this here tells me something like the multinomial. So I have that xk less than xk belong to the interval I, which is x minus epsilon and x plus epsilon, implies that k minus 1 of the n trials are less than x minus epsilon, n minus k of the n trials are bigger than x plus epsilon, and one of the trial is between x minus epsilon and x plus epsilon. So this is like a multinomial with n trials, and the probability P1 is equal to f of x minus epsilon. P2 is between x minus epsilon and x minus epsilon. So this is property that x belong to the interval I. And P3, which is 1 minus P1 minus P2, is 1 minus f of x plus epsilon. So therefore, in that case, the multinomial will say that the probability is given by the multinomial event, which is n factorial, divided by k minus 1 factorial, 1 factorial, n minus k factorial. So therefore, you have k minus 1 factorial and n minus k factorial, because 1 factorial doesn't matter. This is P1, this is P2, and this is P3, which is 1 minus P1 minus P2. So we get this as the multinomial, so P1 and P3 by the multinomial distribution. So therefore, the probability that xk belong to the small interval. So to get the PDF, you can just take the derivative, or you take the limit as epsilon goes to 0 of the probability that the xk, the k of the statistics, is in the interval I, divided by the length of the interval. And if that's the case, that as epsilon goes to 0, the first term, P1, converges to fx. So you get fx of k minus 1. The second P3 will converge to 1 minus fx. So you get 1 minus fx and minus k. And then the third one, which is just fx plus epsilon minus fx minus epsilon divided by 2 epsilon, which is converged to little fx. So what's what you have here. So that is another way to derive the PDF for the kth order statistics. So let us now move on to discuss the joint CDF for xk and xl with k less or equal to l. And the trick is simply, once more, the use of multinomial distribution again. So for given x and y, if x less than y, then the probability that the kth order statistic is less than x and the nth order statistic is less than or equal to y can be written as at least k of the trials is less than x, and at least L of the trials is less than or equal to y out of these n trials of the multinomial experiment. And so at least k less than x, at least L less than y, you can think of it as summation over R from k up to at most L, because k less than L, and S can go anywhere from L up to N. So exactly R less than X, R can go anywhere from K up to L, and exactly S less than or equal to Y. So S go from L up to N. And each of these here is a multinomial probability. So that is N factorial divided by R factorial, S minus R factorial, M minus S factorial. For the three possible probabilities, P1 is less than or equal to X, which is Fx. P1 equal to Fx. P2 is Fy minus Fx. And P3 is 1 minus Fy. 3 trials. So Fx to the power of R, Fy minus Fx to the remaining S minus R, and 1 minus Fy, M minus S. So this is the multinomial coefficient. This is the multinomial probabilities. If x is bigger than y, then obviously xk less than x and xl less than y. Because x is bigger than y, xk has to be less than or equal to xl, has to be less than or equal to y. That's the same as xk less than or equal to y, xl less than or equal to y. So I have to fix this one here. A few typos. So check your note, it will be more clear. And this is nothing more than the probability that xl is less than or equal to y. Because if the L order statistic is less than y, then the k order statistics is obviously less than y if k less than L. So in this case, we have derived the CDF, the joint CDF, for xk and xl. And this works for both the discrete and the continuous case. But once again, if we want to talk about the joint PDF in the continuous case, then we can just take the partial derivative of this previous expression, first with respect to x, then with respect to y of the above quantity. So if we note that if we take the derivative of this quantity with respect to x, that's going to be 0. So d over dx of property xy less equal to y is going to be 0. So therefore, we need the constraint that x less than equal to y in the joint PDF. But in any case, after some tedious calculation, you could show that the partial derivative of the sum turns out to be this messy expression, which is theorem 6.6. That is true for x less than equal to y, because like I said, otherwise d of dx of property that xl less than equal to y is equal to 0. So the joint PDF is 0 if x bigger than y. And you don't have to worry about equality, so because the property of equality of 0 is always 0. So we don't have to worry about that. So in any case, this is the joint PDF, and it is obtained by taking the derivative with respect to this expression here. But I will warn you that it is very, very tedious calculation. But another way to see this result, which is a little bit more, say, simpler, but obviously at a cost that the argument only works for continuous random variable, is as follows, analogous as follows. Suppose I consider interval from x minus epsilon to x plus epsilon for the k of the statistics, and another interval from y minus gamma to y plus gamma for the L order statistics. Then the xk belong to the interval ik and xl belong to the interval il. If and only if now I can compute a multinomial with now a few more class. So the first one is P1 is for f of x minus epsilon. So for the case when xi is less than x minus epsilon. P2 is for fx plus epsilon minus fx minus epsilon. So in the case when xi belong to ik. P3 is therefore now go from f of y minus gamma minus f of x plus epsilon. So in the case when xi belong to at least the interval x plus epsilon and y minus gamma. And then I have P4, which is going from y minus f of y plus gamma minus f of y minus gamma, which is the corresponding to xi belong to y minus gamma to y plus gamma. And then finally, P5 is 1 minus f of y plus gamma, which is the same as xi, bigger than y plus gamma. So now I will have a multinomial with 5 outcomes. So then in that case, I will therefore have n factorial, choose k minus 1 factorial, 1 factorial, l minus 1 minus k factorial, 1 factorial, and then n minus l factorial. So this 1 factorial doesn't matter. So I have n factorial and k minus 1 factorial, l minus 1 minus k factorial, and n minus l factorial. And then I would write x minus for x minus epsilon. So that's P1. This is P2. This is P3. This is P4 and this is P5. And as I say, number of trials out of these n events with this property. And so now if I take the joint PDF, then obtains follows by taking the partial derivative with respect to x and y. That's the same as taking the limit as epsilon go to 0 and gamma go to 0. So as epsilon goes to 0, P1 will converge to fx. And then P3 will converge to fy minus fx. And then P5 will converge to 1 minus fy. The remaining quantity will converge to the remaining, which is P4 divided by 2 epsilon, will converge to little of fx, and not P2 divided by 2 epsilon converge to fx, and P4 divided by 2 gamma converge to fy. And that will be what we claimed earlier to be this expression here, which is theorem 6.6. Okay, so that is another way to see that argument. But in a sense, it is, you could discuss which one you think is simpler. This one may be simpler to think about, but it's harder to take the derivative. This one is easier to take the derivative, but it's harder to think about. So one man's goat is another man's mud. But in any case, using the same trick, we can obtain the joint PDF of all the n order statistics in the case whenever the xi are continuous random variable. And the main thing is because they are continuous, the probability that a value xi equal to a value xj is always equal to 0 for all I not equal to j. So we can therefore take the value x1 less than x2 less than xn, none of them are equal, and then consider intervals around each of these xi. So each of the xj minus epsilon j, xj plus epsilon j. Then the probability that the first order statistics is in I1, the second is in I2, and the n statistics is in In is now the multinomial trials, and this is the multinomial probabilities. So this is once again the multinomial distribution. And so to get the joint PDF, we just have to take the derivative of each of these quantities. So that's the same as taking the limit of epsilon 1 equal to 0, 2 equal to 0, n equal to 0 of this joint probability and divided by the width of each of this interval. So 2 epsilon 1, 2 epsilon 2, and so on and so forth. And as you can see, because of this n factorial here, you will get n factorial. And each of these limit will give you fx1, fx2, and fxn. And that gives you the joint PDF for the order statistics as given here. So that, in a sense, concludes all the materials in 421 and in this class. So I think we have covered quite a bit of material. Maybe not as much as we would want in some case, but maybe more than what we like in some other case. So hopefully some of this will turn out to be useful for you in your 422 study. And in any case, please send an email if you have any further questions. Your take-home exam will be, your take-home final exam will be posted, I think, at the end of this month. So with that said, thank you for your time, and I will look forward to maybe seeing some of you again in person once school come back in session. So take care. Bye-bye.